them energy to fly around the galaxy. So it is possible on the Earth to make antimatter. It's a little more difficult to store it safely, and but it's not, it's not likely to be a solution to the energy problem right now, unless we learn how that there are extra dimensions and we can tunnel and take shortcuts to places where there's a lot of antimatter and bring it back and just, careful engineering control, right? It's sort of like some people are worried about nuclear power, but it's very relatively safe. People are more worried maybe about fusion power, thinking the sun is close enough. But as you go to more efficient energy sources, you have to be more safely engineered. But it's certainly a possibility that that might happen someday. It isn't going to happen right away in time to solve the oil shortage, right? It's a little longer away than that, unless something really spectacular happens very soon. Right? Yes.
Hello, sir. Very good afternoon. I'm Rizwan Mumtaz. I'm a postgraduate student in electrical engineering. My question was just related to the experimentation methods that you usually basically carried out in astronomy or so. Like you also mentioned in your talk that it takes almost billions of years for the light to travel all the way from the space and to reach the Earth. So my question is just the information that we extract from the light or the images that we take of the galaxies and the many objects in the universe, isn't it a bit too old? I mean, how can we accurately predict the nature of the universe that exists today? Or maybe we speculate the nature of the universe that will exist in future. I mean, how does the credibility of this information comes from? Do you take any extra features or the factors into consideration of today's world before predicting something about the today's nature of the universe based on that previous knowledge or the information that is very old?
Okay, so there's many parts to the question, and I'll answer it fairly simply. The thing that's difficult to get used to is that on a human scale, the universe doesn't change very much. So for a long time, people thought the universe was static because on the entire history of the human race, the stars hadn't changed very much, and they hadn't understood that anything could be changing. And so even though it takes light 2 million years to get here from Andromeda, it actually takes, on the scale of 100 million years, for the sun to orbit around our own galaxy. Right? So the time scales that go on in the universe are extremely long. And so if I wanted to know what's happened in the last few minutes, my sample of the universe is no further away than a radius to the sun. Right? But if I'm willing to average over millions of years, right, tens or hundreds of millions of years, then I have a sample that has a fairly large amount. And so now it becomes a question of quantitative. And then you might ask, well, what has happened in the intervening time that may have affected the light that's traveling here from a great distance? And the answer is, to first order, that light is unaffected. The only thing that affects it is its wavelength gets stretched by the expansion of the universe. That's because the universe is nearly perfectly uniform. That is, it's nearly as perfect as a perfect sphere of marble or a billiard ball for parlor games. It's extraordinarily uniform, and so the expansion is very uniform, and it stretches the wavelengths extremely uniformly. It's only when you get to the part in 100,000 you start seeing small variations. Most of those you see in the early universe, and now more than a factor of 10 down below that, you see the effect of intervening clusters of galaxies and the gravitational bending. That's a very small effect, but the fact is we're now trying to go with the third generation satellite to measure things so precisely we can begin to see those second order and third order effects in order to learn about the intervening history of the universe. So we want to see the light coming from the beginning of the universe passing through the matter, by the matter in the dark ages and so forth. And the primary effect is gravitational bending of the light, not absorption or so forth. It's very rare that the light gets absorbed or scattered. It only happens on a significant scale when you go through a very rich cluster of galaxies with a lot of hot gas in it. Then you might get as much as 1% of the photons being scattered, but they only get scattered. They don't get absorbed or whatever. They get scattered to different angles. And so you get another view of the sky. You get a chance to sample what the universe looks like, with light coming in around that cluster of galaxies and some of them getting scattered to you, you can check to see what things going on. So we worry very much about that. We worry about it because it might affect what we're learning about the early universe, but we also worry about it because it's a way we can learn something about what's happening in the in-between times. And so we study that and we think about that very much. And in some ways, the universe has been very kind to us that those effects are very small, but that they're just big enough that we may now be able to use them as a tool as we get more and more precise. We may be able to use the second order effects. It's like you're doing, seismic scattering, and there's an earthquake that appears very far away, and there's double scattering, and you can finally see some local structure once you really interpret your data carefully. It's a very much more tricky and requires tremendously careful thinking and very powerful computer analysis, but we're beginning to do that. And you design special experiments to test it. We're designing big telescopes on the ground to look at clusters of galaxies just to look for these kinds of effects. So your question is good, and the answer is nature. The universe has been very kind to us that it mostly doesn't bother us, so we can make the discoveries and make the first interpretation. We can tell what the universe is made out of. By looking at these sound waves, we can probe the beginning of the universe. We can tell what the universe should be going forward. But we know from just seeing these sound waves on the surface, we can tell a lot about the geometry of the universe. We can tell that it's made of dark matter, dark energy, and ordinary matter at the percentages that we have other indications of. But we can now use the second order effects to try and learn about what's happened to the matter in intermediate times. So we're just very lucky that things work out so well. So thank you all. Am I taking another question, or are we closing it?
We are running late of time now.
So would you like to answer one question?
Oh, okay, just.
Okay. My name is Raja Shahzad. I'm a postgrad student in Mechanical Engineering Department. Actually, I wanted to ask a few questions, but I'm allowed only to ask one. Would you elaborate the thing you said about your discovery that it's like seeing God? So can you please elaborate? Thank you.
Okay. So at the time the discovery was made, we knew very limited amount about the universe as a whole, and this discovery let us understand the two measurements: the measurement that this was radiation from the beginning of the universe, and the discovery we could see the sound waves from the beginning of the universe. Meant we knew we were on the right track. We had the it's like first being able to see DNA, right? You have an idea there's this double helix, but you don't know what's on the double helix. Now we're going back and mapping the genome, the genome for the universe as opposed to it. So in some sense, we're seeing the program or the plan for the creation of the universe and the development of the universe being laid out in front of us. So it is really, it's like seeing the handwriting of God telling you how He intended the universe to be created. And so to me, I knew it was very profound because it meant, yes, the Big Bang is correct. Yes, we can see structures. With these structures, we will have the tools to understand how the universe developed and understand what it's made out of and how it's going to develop over time. And so far, in the intervening 15 years since that discovery, well, it's more than 15 years now, 16 years, we have started to fulfill that promise. We've got much higher resolution maps. We've got better simulations. We've got good understanding of what the universe is made out of. We understand the geometry of the universe. And we have multiple ways of seeing that and understanding and checking that what we're seeing. So it turned out, it felt that way, and it turned out to be that way, that it really sort of is given the key to reading the secrets of the universe.
Thank you, Professor, for sharing with us your experience and insights. It has been a beneficial session for all of us. Now we'd like to invite Yang Berbahagia Dato Dr. Zainal Abidin Haji Kasim onto the stage to present a token of appreciation to Professor Smoot. Thank you Yang Berbahagia Dato and Professor Smoot. On that note, we have come to the end of today's program. We hope that everyone has benefited from this session. Ladies and gentlemen, please rise for the national anthem.